Welcome to Superheroes of Science. I'm Stephen.
And I'm Sarah. We co-host Science from the Experts. Our guests are professionals doing cutting-edge science right now.
They're experts in their field discussing what they know best. So listen up and learn real science from real people.
Subscribe now and stay informed of our latest episodes and show your support. Today on Superheroes of Science, we're here for a special episode with Alex Wei, professor of chemistry here in the Department of Chemistry at Purdue University. And we're here to talk about Alex's research with making materials that interact with light and produce light. And we're excited to learn more about this. So thank you for inviting us and joining us.
Oh no, it's a pleasure to be talking to you today, Sarah.
Yeah. So you make materials that interact with light.
Yes. So we are synthetic chemists, right? We make molecules, we make nanomaterials, and one of the things that they have in common is that we like to study how they interact with light. And so some of them are good at absorbing light, and some of them are good at producing their own light, like a fluorescence or a luminescence. Okay. These what we call photochemical processes or photophysical processes are really kind of the heart at what we're trying to study.
Okay, and so you say some materials absorb light, and some of these materials maybe produce light, like in fluorescence. What's the difference between like absorbing light, or sometimes we'll hear reflecting light, or can you speak a little bit?
Sure. Okay. So yeah, I think it comes down to a lot of basic ideas of how we interact with light every day through our eyes, right? So let's talk about color,
okay.
Right? It's an easy way of doing it. And so the classic example that we often like to talk about in chemistry classes is that you look at a leaf, right? What color is a leaf? The leaf is green.
Right.
But is the leaf actually green? Is it producing green light? And the answer is no. So what a green leaf does is that it reflects light from the sky, right, into your eyes that is green. And in order for it to do that, it actually absorbs a different color of light, which turns out to be red. So it's not that the leaf is producing green light, but it's reflecting green light from the sky into your eyes.
Got it. Okay. And then you said that you work with nanomaterials.
Yes,
that's
right.
What is a nano material, or what is that nano?
Yeah, well, it all started, I would say, maybe 20, 25 years ago, that people realized that if you take a bulk material, let's say gold, okay, right, and you cut it down to really, really small particles, right, so, much smaller than human hair, much smaller than your cells, then they will eventually get to a size where they interact with light differently than the bulk gold. So we know that gold is yellow, right? My wedding ring here, right, reflects yellow light. But other kinds of gold do not. So I actually have a couple of samples I can share with you, if you'd like to take a look at them. Okay. So here's actually two of them. And these, believe it or not, are both solutions of gold nanoparticles. They have different shapes and sizes. This one, which looks like a wine red solution or fruit punch, depending how old you are. This actually contains particles that are about 40 nanometers in diameter. So that's like 7 orders of magnitude smaller than maybe the size of my ring. So these are really small. And because of their size, they have this special property. It's known as Plasmon Resonance, that actually is really good at absorbing green light in this case. But we don't see the green, because what we see instead is the red light that is reflected into our eyes. Okay, but these absorb at a particular wavelength, and these also are gold nanoparticles, but they are of a different shape. These are instead of spheres like these are actually rod shaped. Okay. And this is they do something that our eyes cannot see. So what we are looking at is a purplish solution, but actually these particles are able to absorb light past the visible wavelength into the infrared. Oh. And so, and that's very useful from a technological point of view, because oftentimes people want to use infrared light to penetrate into the skin and look underneath what the skin is. And so these particles are good at absorbing it. They can be found under the skin should you use these as some sort of detection agent.
That's very, and so is the shape of those, you said some are spheres and some are rods, is that contributing then to the color that we see?
Yes. So of course the details can get very hairy, but in a nutshell, the shape of the particle control how the electrons inside the gold bounce around, and it's the way that the electrons resonate, right, that actually give us the ability to see what is going on. And so in the case of these particles, right, the electrons are resonating at this green frequency, right? And although we don't see the green, right, what we see instead is this red color. That's because the light is being absorbed. The green light, I should say, is being absorbed by those particles. They're exciting the electrons in those particles. And then the near-infrared light, which we don't see, right, is doing the same thing here. But the result of that is what we see left over actually turns out to be this dark purplish type of color. Yeah, so so this is really actually a very fascinating field. Silver can do this. Other kind of metals can also do this. Now there are all kinds of new sort of materials. They're not even metals anymore that also are able to have these electrons that are excited that can interact with visible light or near-infrared light and so on. So it's a huge area actually. Great technological potential.
Now you had mentioned luminescence and fluorescence. How does that? How is that factoring into what you're doing?
Okay, yeah. So if I put aside the nanoparticles, right? So another type of material we work with are molecules that they're much smaller than particles. Okay, so these particles, we say that they're on the nanometer length scale, but when we think about molecules, we're really thinking about them on an angstrom length scale. So 10, 100 times smaller than a nanoparticle would be. And because of that, electrons also bounce back and forth inside of many of these molecules, but it's a much shorter path. And for that reason, the rules are different. How those electrons might interact with different wavelengths of light. Okay, so a lot of things that we work with every day, they again can be very strong colors, dyes, for example. I'm thinking of carrots right now, right? Carrots are orange because they have this molecule, beta carotene, where there's this little controlled path that the electrons bounce back and forth when a certain wavelength of light hits it, blue light in this case. And what we see instead of blue is orange. Okay. And then of course a lot of dyes, right, in our clothing, right? These are made of molecules that have been discovered or even designed to absorb particular wavelengths of light. And they result in the color that we see. And then there are fluorescent materials, right? And I think we've all heard about fluorescence. And that now gets to the point where we're actually asking the molecules to produce their own light. Okay? Which is a little bit different from reflecting the light or scattering the light. So we actually can excite the molecules, and they will produce a particular wavelength, and that is crazy useful.
So how is this happening?
Wow. So,
but I guess in a basic sense, are the materials that produce this light, are they exposed to a light? Like I'm thinking of, maybe those stars that you could put on your walls when you're little, and during the day they get some light, and then
those
at night
glow
they
in the dark stars, right? Yeah, we still have those in our house too.
Okay.
Let me. So let's come up with a few terms here that will help us explain. So this property in general is called luminescence. So luminescence refers to the idea that a molecule or a set of molecules can absorb a particular wavelength or frequency of light. And the electrons in that molecule then go into what we call the excited state. And they don't stay there very long. It's only for maybe a couple of nanoseconds in some cases. Or in the case of glow-in-the-dark stars, maybe they'll stay up there for a few minutes. But eventually those excited electrons, we think of them jumping up, will fall back down, right, to what we call the ground state. So going from being excited, right, you always have to come back down to Earth. So that's what these electrons do. And when they do that, then they release a photon of light. And that photon is defined by how far they have to drop from the excited to the ground state. Okay, so that's the basis of luminescence of all kinds of things. So molecules, polymers, even nanoparticles can produce luminescence. Okay, with me?
Yes.
All right, great. So now we have two different categories of luminescence. So let's talk about one that we work with all the time, right?
Oh, yes.
And that is fluorescence. Okay, and so here I got in my hand this highlighter pen, right? And we take some text, right? We draw lines, and you'd be surprised to know, and many people will be surprised to know that actually it makes the area that I just colored brighter. Okay, and that's not just simply because we put on some kind of yellow paint. It is brighter because it is picking up certain kind of photons, right, from the fluorescent lighting, for example, or just the outside lighting, and then it's actually producing yellow light in this case. Okay, so that's a little bit different from the example we started with. We talked about a leaf that was green.
Yes.
It doesn't produce green. It reflects green. But here, my highlighter pen, right, actually produces an ink that really does produce a yellow light. So it's probably more than just yellow, but for today, let's just simply call this yellow.
Okay.
And so these fluorescent inks, right? They're again these organic molecules, mostly dyes, that have been designed to, when you shine just room light on it, right? The electrons get excited, and then they come back down pretty quickly. But then they produce a light that we appreciate, and now it's actually producing its own light. Yeah. How do you know that it's that this is fluorescent and not some other just simply reflection like a leaf, right? And so what we often do, and I wish I had one, is if we turned out the lights in the room, right? We take this black light lamp, right, and you shine on it, and then you can really see that it's glowing yellow, right? And so that for sure is a telltale sign, right, that that's a fluorescent material. A leaf wouldn't do that for you. It won't glow green, right? It'll just look dark, right? But anytime you have a fluorescent material, it'll produce this color, right? Or whatever color it's designed to.
Yeah.
Yeah.
Definitely.
Okay, now back to those stars,
Yes,
right? Yeah,
right.
so those glow-in-the-dark stars or other kind of things. So now they have, so let's talk about a different category of luminescence. So that's fluorescence, right? Those glow-in-the-dark stars are what we call phosphorescent materials, okay? And so the difference between fluorescence and phosphorescence is mostly about the time it takes for that excited electrons to come back down to the ground state. And so of course it can be useful, like if you are carrying around those glow light sticks, right? Oh, I'm sorry, that's a different area. I shouldn't touch that. We'll go back to those stars.
Okay, go back to the stars.
Sorry about that. Yeah. So if you just want to be able to see like the hands on your watch for those who still use watches, right? They have these glow in the dark arms, right? So you can see. So that's useful because when it's dark, you need something to see for a long time. So the way that works is very similar to fluorescence with a little extra catch. Okay, so the first thing you do is that it absorbs light and it gets excited, and then instead of coming back down, it actually moves over to what we refer to as a triplet state. Okay, and so to explain that in a little bit more detail, electrons or I should say the molecular orbital that electrons sit in, are generally singlet states. Okay, we don't talk about them as singlet states because they're almost all singlet states. But there's also orbitals that are triplet states. And this really gets buried into issues of molecular symmetry or orbital symmetry. Okay? But the thing about singlet and triplet states is that they usually don't mix, right? Singlet sticks with singlet, right? Triplets will stick with triplets, and the two hardly ever cross. But in the case of phosphorescence, right, they break the rule. So when you excite a molecule, right, it's excited singlet state, there are ways for it to kind of crawl under the door, right, or under the fence and get into the triplet world. And there they will sit, and now they can't get back to the singlet world very easily, right? So kind of like almost like a one-way route. Okay? So they're trapped in the triplet state for, well, not forever, but for a good long time, right? It may seem like forever to the photon or the electron that's trapped. But eventually, right, something will happen. The planets will align, so to speak. And then finally the electron can come back down to the ground state, right? And when it does, then it produces a light. And that's, on an electron's point of view, very long delay. And to us, that's like delay of seconds to minutes, right? And that's how we can see that. So So the reason that you have these glow-in-the-dark stars is that, okay, so you have a bunch of trapped electrons, right? They're excited, but they're triplets, they're in triplet state. They can't come down, but slowly, right, gradually, they're able to get down to the ground state and release a photon. So what we see are stars that are pretty bright in the beginning, right? Just turn off the light room, the room light, and they glow well. But you notice after about 10 minutes that they're starting to really dim out.
Yes.
Okay, and so basically we're running out of electrons that are trapped in that triplet state. They come back down. So you can start all over again, turn the room light back on, right? And then you excite them all again, and and just keep going forever if you want, right?
Yeah.
Or until you get bored or fall asleep.
So it's very, very interesting to hear you talk about the electrons then getting exposed and going to an excited state and then falling back down to the ground state. So that that we see that as light given off then.
Yes, that's right. Yeah. So one thing to keep in mind when we're talking about all of this, light's a form of energy. And so when you absorb a photon of light, right, you're picking the molecule, in this case, is picking up energy. And so so when the electron's coming back down, it releases a photon, right? So it loses the energy that way. Okay. And so oftentimes when we absorb light, like if we're out sunbathing, for example, right? How come we don't glow, right? Well, I think it's a good thing that we don't. If we did, we'd probably have to see the doctor.
Right.
But when we absorb light, we don't. Electrons maybe get excited in a different way, but they don't produce photons, right? Instead, they actually produce heat. So actually, most of the time when we excite electrons, generally speaking, we generate heat, okay? And that's how we lose our energy, okay? And we know this, right? Go out in the sun, we feel hot, okay? And so only a certain class of molecules or materials, right, can actually be able to absorb the light and then convert it back into another form of light.
I see.
So that's special from our point of view. That's special.
Where are some places in our everyday life that we might find like fluorescent materials? Or I know we talked about the glow-in-the-dark stars, but are there other applications that?
Okay, so let's see. Well, the one that comes to my mind is something that maybe is not in every house yet, but maybe in about 5 years, right? We'll start to see a lot of these, and that is the next generation of TV displays or flat panel displays. So right now we have our normal flat panel display. When we turn it on, we're generating light the way that we normally think that we produce light. Okay. And you'll notice that they still get kind of hot, and so they're not efficient in that manner.
Right.
Okay. And one of the problems of working with these kind of screens is, or even our laptop screens, is that the light is actually on all the time, right? So even though it's black, right? Even though we have a black background here, right? There's still some light getting through it. Okay. And so we have what's often called the blue light syndrome, right? You might have heard about this. Okay. This is not really evil. It's just that if we stare at our TV screens or computer screens too much, we get too much blue light from the backlighting, it's called, and it kind of messes up with our sleep patterns. I'm experiencing that now this week as I stare at my screen too much. Okay, so there is a new technology that will reduce this blue light problem, and also improve the energy efficiency of these screens. And this is known as OLED. Okay, and OLED stands for Organic Light-Emitting Diodes. So OLED technology was maybe invented right around the turn of the millennium, in the early 2000s. People already started knowing about it, but now the technology, fast forward 20 years, technology is now here in the form of new types of TVs, new type of laptop screens, smartwatches have OLEDs. So it's actually already here, and we don't always actually know about it. But it turns out that these OLED screens are, much better for your eyes, for one thing, right? They're much brighter, the resolution is better, the contrast is better. And so that is a new form of light-emitting material that we'll be surrounded by in the next few years.
That's awesome to hear about that. Very cool.
But the organic, when you say organic, I mean, is it like glow-in-the-dark bunnies inside there? I mean, what's the organic part of that?
So Steve, you're asking. Now we're really getting into the weeds.
Yeah, sorry, I just couldn't help but ask.
Okay, so of course, there's a variety of different materials that can provide the light emission for these OLEDs. Okay, and most of them are, some of them are indeed small molecules. Okay, like fluorescent dyes, and some of them are actually nanoparticles, right? They're called quantum dots, and some are polymers. And actually, it's the polymers that seem to have the maybe the best success right now because they are more robust, they're bigger, right? And so they can take, they can take more hits, I guess. So people are still designing materials, and then there's kind of combinations, right? So mixing organic molecules and inorganic elements, right? They're finding that this works very well. And that actually now comes into an area of research that we've fallen into. And we found that we have these special complexes where we mix a small molecule, it's called a pyrazole, and copper atoms. And when we mix them together, they form this really cool complex that just kind of crashes out a solution that we can pick up. And wouldn't you know it, it produces this beautiful blue light, right? And that is, and that's very exciting to us. And it's a blue light that would be of interest to OLEDs because it's something that OLEDs are still, or the technology I should say, is still working on, right? OLEDs are good for can produce red light and green light very well, but the blue light's a bit troublesome. The efficiency is not quite there yet. The energies the energy required to produce it is a little bit higher. They burn out faster. So there's this global search for new type of materials that can produce deep blue light. Okay, and I just got through telling you that we have this blue light syndrome with these screens, but OLEDs have the opposite problem. They don't produce enough blue light, and we would like the blue light to, of course, have our full range of visual displays. So, of course, we do have OLEDs that do produce it, but they burn out faster, and so they're looking for more robust materials that can produce the blue light. And so that's actually the heart of the current research project that we're working on. The molecules, since we're talking about chemistry, the molecules that we have are really cool looking, just from a picture, just from a structural point of view. And just give me one moment here. Sure. So what I'm building is this complex where the red atoms, these red structures, these are copper atoms, okay, and they're bonded together by these blue pentagons, okay, and it's not atom accurate, but basically these pentagons are molecules known as pyrazoles, and there's other things off of the pyrazole, but this is the basic structure. Okay, and so by mixing together, the 4 pyrazoles hold together these 4 copper atoms, and they have this, they're not flat structures, although if you look at it like this, it might kind of look flat, but actually, right, it has this cool saddle-shaped structure. And this is one of the fun parts about chemistry, right? We might not have predicted that by mixing together copper atoms and a pyrazole that we would get something as fancy looking as this, but sure enough, right, this is what comes out of solution. And we've been studying this, and what we have learned so far is that the blue light produced by this molecule are based on how close these copper atoms are to each other. Now, sorry that the copper atoms are red. I wish they were blue, but to make the story a little bit more concise. But basically, by bringing the copper atoms together, their atomic orbitals, molecular orbitals, actually combine into what we refer to as a closed cluster state, and so basically it becomes a superatom, right? These 4 copper atoms act as a single unit, and you can excite that single unit, right? And it produces those electrons get excited, and then they come back down, and then they produce, they luminesce, right? At a blue wavelength, okay? And that's great, right? Because that's exactly what we want. And so we're learning how to design structures very similar to this to continue to produce, even stronger blue light, or maybe even push that wavelength farther up past the visible into the ultraviolet. We want to be able to create networks out of these sort of structures. So that's where that research is going. Ultimately, we hope, maybe ideas like this will eventually end up in somebody's OLED TV screen, but we can't promise that yet.
Now, why, can you speak about, so you said red light and green light they have. Why is it important then to add that blue light in for an LED?
I'm sorry, I guess I did skip that part. So this really comes down to, how should I say, digital technologies, right?
Okay.
How people in the optics world have trained us to see light. Okay, and so in our TV screens, even from many years ago, usually we can make up any color that we can see in the visible light spectrum by mixing the right amount of green, red, and blue. Okay, so you'll hear RGB bandied around when people talk about this. So the right mixture of R, M, G, and B, right, can produce yellow, purple, white even, right? So it's possible to get white light with just the right mixture of those three, right? Different intensities, different hues. Anybody who's like a graphic designer is very aware, of how we are able to do this, okay? And so, but it all boils down to those three, right? And so there is this community that's kind of defined, right? Here are the three exact wavelengths or exact colors that we want to be able to generate the maximum range of colors that our eye appreciates. To answer your question about RGB a little bit better, right? So when you have, this is what's known as the Cie Color Coordinates.
Okay.
And so each one of these colors, each one of these spots within this thumb-like structure represents a certain amount of intensity of red, green, and blue. Okay, so of course this is like almost all blue down here, right? And this is all green and all red, but you can get everything else in between, right? And so it's kind of surprising because yellow, orange, which we appreciate a lot, it's actually a very narrow part of the spectrum, but it's easy to mix these two to get all the different shades of yellow and orange, right?
Yeah.
That we like to see. The hardest part is actually boxing over here, right? So getting the very edge of the visible spectrum, what we call the deep blue range, still has been somewhat problematic. And so you can see here, I don't know if you want to share this with your audience, but a few years ago, right, they were talking about, we've got plenty of good materials for red and they last very long, right, and good materials for green, but blue, we don't have good materials, right, they're not blue enough. And their lifetime isn't very long either. And then more recently, right, just the last couple of years, right, people have been able to get blue emitters, but their lifetime is even shorter. And so we really need to come up with molecules or complexes that also produce this deep blue, but can just last a lot longer inside of the devices. So there's this global search for new kind of things, new kind of material that can produce the deep blue light.
So how does a chemist, when I think of like the next generation of entertainment technology, I'm not thinking of a chemist.
Yeah.
And so I was really shocked when you're like, oh yeah, we're working on the next TVs. We're making these better, and it's going to be better for your eyes. It's going to be better for your viewing pleasure. And I would have never thought about a chemist is who they're working with or who's designing parts of that.
Yeah, chemists are the unsung heroes of today's society, right?
Yes.
I've got to get that in there.
Yes.
Okay. But to be a little bit more fair, more balanced, it takes a village, right, to develop something that is truly useful for everyone. So, chemists, to be honest, didn't come up with the RGB idea, right? What chemists are really good at least in this context, is discovering or designing, right, new materials that can help meet a particular criterion. Sometimes, they're due to just a chance discovery. I have to say that, this was, for us at least, a sort of a serendipitous discovery. We didn't expect to make this in the beginning, it just kind of fell out. But we've turned it now into a scientific project, and so being very systematic about it. So stuff like this, right, often, spurs new ideas, right? And we find, oh, here's a good application for this material. It's the OLED world, right? And sometimes there's something that is so weird wonderfully weird that there is no application, but then somebody else sees it and they say, oh, maybe we can try to do something nobody's done before.
Yeah.
And I think that's really the magic of something like chemistry, where you can actually make a material molecule that's never existed before, right? Never characterized, at least, and then find out some novel property, right? And it might help with an existing problem, right? Or it might lead to something that nobody ever thought of before. And it's exciting to think about it in those terms, right?
Yeah.
Absolutely.
Yeah, I would tell my students, chemistry is the closest thing we've got to magic. Right? Take stuff off the shelf, mix it together, right? Boom, right? I mean, it's not a rabbit, but right?
Yes.
I got this.
Yes. So did you, were you working, all right, so when you've discovered that this worked, were you, before your, I'm going to call it discovery, were you working towards this, or did you realize this would, when I say this, were you working towards this technology, advancing the technology, or did you realize the discovery would help it?
Yes, so here's part of I got to tell the human part behind this story now, okay? And so first I want to say that this was not my idea. Okay? I'm really just the front man for talking about this. Well, I'm sharing the idea now. But this was really due to the efforts of two people in my research group. So one was a graduate student who made this complex, whether by accident or not, right? He made it. And the other was his neighbor, his lab mate, who's now a professor, an assistant professor in Kyoto University in Japan. And he had this background. He got a PhD in organic electronics of materials just like this. He wasn't working on this in my lab, but he sure knew a lot about them. And so when he saw this type of complex, he told my student Ben, this is Ben and Eurytro, that's their name. So Eurytro told Ben, I bet we could design something that can produce a blue light. And so that's what led, in fact, to this complex here. And then they kind of ran with the ball. They just started studying it and finding out all kind of cool things. First of all, it's got this nice weird saddle-shaped structure, right? Secondly, they found they produced really wonderful blue light. The third one, we have another molecule that switches between green and blue light depending on what you do to it, right? Oh. So like every couple of months, right, something new pops out from this, from what's really a very simple system in the beginning, right? But we're finding this cool complexity, this chemical complexity leads to, right, these new light-emitting properties, right? Yeah. So one molecule that's complex, very similar to this, but just has some extra groups on it. If you expose it to gasoline, it'll go from blue to green. It'll go from being blue emitting to green emitting. You should be careful when we say blue or green. So it emits blue light, but upon exposure to gasoline. But when you heat it up, right, it goes back to being a material that emits green light. So and back and forth it goes. And so we've been studying why it does that and how it does that. And that's probably a story too long for today, but that's the kind of thing that really we really like to study. To turn this into a real technology, I think takes collaboration. We would need to find engineers who have a very strong interest in exactly this sort of problem, and they would say, hey, I will take your material and try to make a device out of it, and let's see if we can run some electricity through it and if it will produce blue light. That would be great. Haven't found anyone yet, so anyone who's listening, right, knows somebody that would like to do that, have them give me a call.
Looking for collaborators.
Okay, but yeah, so that's why I say it takes a village to really, to do these developments. But a lot of cool things along the way as we're just kind of working toward. Now I think we have this goal of really just understanding how to make more robust materials that somebody might indeed someday want to pick up and say, I'm going to try to turn this into something for blue light on OLEDs. We would like that.
That's awesome.
That is so. I love that story. I love hearing that and how it applies, and that it applies. You found a way that it might apply to something.
Oh, I forgot to mention that all this happened during COVID. And so this was a time when it was very hard to communicate. We were locked out for 3 months. We had lockdown. And so I don't know exactly when this discussion started. I was out of the picture, right? Everybody was just hunkering down. So this is some behind the scenes work going on. And finally, when we got together again, they decided to do a reveal and said, look what we've got. And what could I say, right? I can't say, how dare you, don't work on this anymore. I say, this is really interesting, let's keep going.
Yeah, it's definitely. That's awesome. Wow.
Well, excellent. Well, we sure enjoyed just talking to you and being here and being able to see some of these things in person is great. Thank you for listening to this episode of Science from the Experts from Purdue University's Superheroes of Science.
If you like this episode, subscribe, give us a positive review, and share the love. Boiler up!
Hammer down.